Now let us discuss the ideal gas law. All four properties of gases, that is pressure, volume, number of moles, and temperature in Kelvin scale, can be combined into one single equation called the ideal gas law, which is why I use this to determine the equations, expressions needed for Boyle's law, Charles' law, Avogadro's law, Gay-Lussac's law. They all stem in here. R is the universal constant. Usually the number for R is 0.08206 with SI units of liter, atmospheres, mole per Kelvin, which is why our volume must always be in liters, our pressure must always be in atms, our temperature should not be in degrees Celsius but should be in Kelvin scale. And then of course the amount of gas, we're talking about gases, should be in moles. So the SI units of the R constant dictates the SI units of our parameters. Now, if we were to use the pressure in millimeters of mercury, then it would be 62.37 liters millimeters of mercury in place of atmospheres, then per mole per Kelvin. But I'll have you know that the one we preferably use is this one, 0.08206 liters atmospheres per mole Kelvin. Let's look at an example on how to carry out calculations involving ideal gas law. Example 1. How many moles of gas are contained in a typical human breath that takes in 0.5 liters of air at 1 atm pressure and 37 degrees? So we know what we are given. We are given the pressure as 1 atm, volume is 0.5, temperature is 37, and that has to be converted to Kelvin by adding 273 or 273.15 to give us 310 K. We need number of moles, yet we know ideal gas law is PV equals to nRT. So if I divide both sides by RT, RT and RT will cancel here, so our N will be equal to pressure times volume over gas constant times temperature. This is the expression that we'll use to find the value of N. So the first thing we want to do in step 2 is to convert all values to proper units and choose the value of R that contains these units. So since the pressure is written in atmospheres, the version of R we should use is this one, the one with 0.08206. Okay, and temperature has to be converted into Kelvin from degrees Celsius. We add 273.15. People who assume a lot will just add 273 because it's an estimate, but the best is to add 273.15, and the answer here would have been 310.15. Now let me see, 273.15, if you add 37, it's kind of, we are cutting here. That's the rule of addition for significant figures. So you'll have 0.15, 10, 310. So we drop the rest because here 1 is less than 5, so which is why the answer is reported as 310. The value for R, like I said, is this that we are using because our pressure is in atm. We were given P to be 1 atm, so we go with this version, don't go with the millimeters of mercury one. And then we do know the equation. If we divide both sides by RT, we are looking for N. RT and RT will cancel, so the N will be equal to PV over RT. All that is left is to put in our values of pressure is 1 atm, volume in liters already 0.5, R we're using the 0.08206 version because it has atm in it, and then the temperature is already converted to Kelvin. Okay, it was given degrees, we convert it to Kelvin. Now this is the reason why we need pressure in ATM, volume in liters, temperature in Kelvin, so that the Kelvin and Kelvin will go, and then the ATM will cancel, and then liters and liters will cancel. We are left with moles, which will be our final SI unit. So the number of moles of the gas N using ideal gas law, given the other conditions PVRT, will be 0.02 moles. Let's do two more examples exploring the ideal gas law. The ideal gas law goes pressure times volume in liters must be equal to number of moles times the gas constant times temperature in Kelvin. This question reads, it's not safe to put aerosol canisters in a campfire because the pressure inside the canisters gets very high and they can explode. If I accidentally throw a 1.0 liter canister that holds 2 moles of gas into a fire that is 1400 degrees Celsius, what is the pressure inside the canister in ATMs in atmospheres? So as usual, you want to start with the given. What are you given here, the givens? So I'm given a volume to be 1.0 liters. I'm given N, which is our moles, to be 2 moles. And I'm given T to be 1400 degrees Celsius. So the one thing I want to do is to convert my T to Kelvin scale by adding 273.15 to my 1400 degrees Celsius. And that's gonna give me 1673.15 Kelvin. I know that pressure times volume must be equal to number of moles times gas constant times temperature in Kelvin. I'm asked for P, so I'll divide both sides by V. That way, the V is X'd out, so my pressure will be equal to nRT over V. I'm given moles to be 2. Gas constant is always 0.08206. By the way, this is 2 moles. So gas constant is 0.08206 liters atmosphere per mole per Kelvin. That's a determined number. There's a way to find that even experimentally in class. And the temperature is 1673.15 K. I'm going to divide all these by my volume, which is 1 liter. Now, doing so, you realize that some units will cancel out. The liter and the liter will cancel out. The moles and the moles will cancel out. The K and the K will cancel out. We are only left with ATM, which is why our units must match the SI unit of the R gas constant, so we can have some cancellations. So my pressure P is gonna be equal to, let's do the math, times 1673.15. I'm dividing this by 1. So it's 274.597. I should stop there. And this one is in ATMs, the units that were not cancelled. Now, our question has values. I think I'm seeing the value as one significant figure here. I can leave it to one significant figure as 300 ATM estimated, because I see I have 2 moles here. Or write it as 3 times 10 to the power 2 ATM. Whichever the case, just report your answer to the said significant figures you are asked to report to. So that's the answer that we found for the pressure using ideal gas law. Let us do another ideal gas law question. In this question, we are asked at 1.28 atm, 145 grams of carbon dioxide has a volume of 34.13 liters. What is the temperature of the sample? So we are given a pressure of 1.28 atms. We need that in atms. We are given a volume of 34.13 liters. We need the volume in liters. The problem comes where we are given the amount of CO2 is given in grams as 145 grams. We need it in moles. So the first thing we want to do is to convert that to moles. Okay, to find the molar mass of CO2, we need to determine the atomic masses of carbon, oxygen, and oxygen from the periodic table. If you look at the periodic table, the molar mass of carbon is 0.11, at least for the one I have. Each oxygen is 15.999. 15.999. If you've forgotten how to find the atomic masses of these in order to determine the molar mass of 1 mole of CO2, I'll remind you to go to the periodic table here. So you can see carbon is 12.011 right here, and oxygen is having an atomic mass of 15.99. Don't go for the smaller numbers. Those are number of protons. Those are atomic numbers. So now you know how to do that. So now let's add these up and see what we get. 12.011 add 15.999 times 2. Okay, the answer I'm getting is 44.009, and these are grams for each mole of CO2. Now, since I'm given 145, I want it in moles, not in grams, so I'll use my dimension analysis process. I'll convert these grams of CO2 to moles of CO2. I know for every 1 mole of CO2, it has a mass of 44.009 grams. We got that from our molar mass calculation. Doing so, G of CO2 and G of CO2 will cancel. Our answer should read something moles of CO2. And we can divide that. So we'll say 145 divided by 44.009. The answer I'm getting is 3.2947 moles of CO2. Can say 478 moles of CO2. Okay, so now that is gonna be my N value. So I have my N value, I have my P value and V value. So now I can find the temperature. On the side, we know that PV equals to nRT in ideal gas law. So if I need the temperature, I'll divide both sides by moles and gas constant. That way, NR will cancel. So my T will be PV over NR. This is the expression that will help us to find our answer. So our temperature is PV divided by NR. Our P is 1.28 atm. Our V is 34.13 liters. Our N, we found it as 3.29478 moles. And then our R is 0.08206 liters atmosphere per mole per K. And that will help us to cancel out some things. Okay, so I believe ATM cancels. Liter and liter will cancel because that's going all the way. And then moles and moles should cancel. The only thing left is K. And that's gonna be our final answer. So in this case, if I do the math, what do I get? 1.29 multiplied 34.13 equals to divide by 3.29478 equals to divide by the R constant 0.08206. So I'm getting 162.843, approximated 162.843. 278.843 kelvins. That will be the temperature in Kelvin, and I can report it to 3 significant figures at just 162 K. Now suppose you want this answer in degrees. I'll do it aside here. So temperature in degrees Celsius, will take our Kelvin and then we'll subtract 273.15. So it will be our 162.843 minus 273.15. So the temperature in degrees Celsius will be 162.842. I'm subtracting 273.15 to find my temperature in degrees. It's going to be negative 110.31 approximately degrees Celsius. In 3 significant figures, it will be negative 110 point. So depending on the question, how you're asked, that's how you do the math. Okay? If you need the answer in degrees Celsius, I've shown you how to. If you need it in Kelvin, you stop there.